In this math talk, I'm going to build on the last video that I did on scientific notation with large numbers. We're now going to look at scientific notation for small numbers, and we tend to use scientific notation exactly for those sorts of things. For measuring, let's say, the number of stars in the universe or the distance between galaxies, we tend to use scientific notation because the numbers represented in those situations are extremely large. And the reverse of that, when we're looking at the atomic level of matter, and we're measuring, let's say, the radius of an atom or the diameter of an atom, those distances are incredibly small. And so in that situation, we also would turn to scientific notation to help us represent those very, very small numbers. So here, we're going to start with this question. What is the radius of a hydrogen atom? In the last video, I talked about water and the fact that there were 500 trillion water molecules in a tablespoon of water. That implied that each individual molecule had to be extremely tiny if we were going to fit that many into a tablespoon. Well, if you can imagine, water is made up of H2O, or in other words, two hydrogens and an oxygen. Each hydrogen itself must be even smaller than an entire water molecule. So in fact, hydrogen is incredibly small. And the radius of a hydrogen atom is this in meters. And this is an incredibly small number. This is in fact less than a nanometer. And as in the last video, we're going to ask ourselves, is there a more compact way to write very small numbers? This number is incredibly small, and I really don't want to have to write all those zeros. Well, before I get to that, let me go through the same sort of development that I went through in the last video. And I want you to consider a number like 0.07. That number isn't actually that small, and it will help us to develop the strategy we need in order to deal with this very, very small number. Okay, 0.07, if I consider place value, I look to that first zero to the right of the decimal place, and I say that's the tenths column. Then the second column, where the 7 sits, is the hundredths column. So another way to represent this number is to say that 0.07 is 7 100ths, or 7 divided by 100. Well, I can just as easily break up that fraction and write it as 7, the whole number, times 1 over 100. And then I look at that 100 as I did in the previous video, and I say, gee, I could probably write that as a power of 10. And I do in my next step, I say, this is equivalent to 7 times 1 over 10 squared. Now, I also understand from the video that we did on negative exponents that 1 over 10 squared is the same as 10 raised to the exponent negative 2. So this is equivalent to 7 times 10 to the negative 2. That, in fact, is our scientific notation representation of 0.07. We say 0.07 is equivalent to 7 times 10 to the negative 2. It's starting to look a lot like what we were doing with large numbers. The only difference being that our exponent, when we're dealing with small numbers, is a negative. What I want to do is look at that decimal place sliding technique that we developed with the large numbers and use it again for the small numbers. So let's relook at this number and say, okay, 0.07. On the right, I've got that number written again, and I'm going to take the decimal place and now slide it instead of the left, the direction left, which we did in the previous video, I'm going to slide it to the right. And once again, my goal is to get one non-zero digit on the left side of that decimal. All it has right now is a 0 on the left of it. We want a non-zero digit immediately to the left of it. So I'm going to slide it once, so it would look like this. In the process of sliding that to the right, one space, I just made that number 10 times as large. So I have to build in a divided by 10. So effectively what I'm saying is 0.7 divided by 10 is the same as 0.07. Now, dividing by 10 to the 1 isn't the most convenient way to look at it. Certainly it's not scientific notation. So what I do is I convert it to a multiplication and change the exponent to a negative 1. So now I have 0.7 times 10 to the negative 1. Well, I'm still, as I said before, not quite in a situation where I've got one digit that's not 0 on the left side of the decimal. So I have to move it one more place. That would move it to that location, and I would then have to take that answer and divide it by 100. So 7 divided by 100 is 0.07. Well, that 100 can be written as 10 squared, and of course, we're going to turn it into a multiplication, calling it 10 to the negative 2. So, in fact, my final answer, without the zeros written in, because we don't write those leading zeros, is simply this. 0.07 equals 7 times 10 to the negative 2. The left side is standard form, the right side is scientific notation form. So now, let's return to the question that we have above, which is, what is the radius of the hydrogen atom? Well, once again, I'm going to write that number and pay close attention to the decimal place. Right now, the decimal place is sitting well over to the left, and I need to locate it so that there's one non-zero digit on the left-hand side of the decimal. So I'm really looking to move that decimal place so it sits between the 2 and the 5. So I've opened up a space there for it. Now I just have to move that decimal. In the process, as I slide that decimal, I'm going to count how many spaces I move, or how many digits I move past. Here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I moved past 11 spaces, so I must build in times 10 to the exponent negative 11. It's negative 11 because I was sliding that decimal place to the right. Now, of course, I'm not going to finish with my answer looking like that. I remove all the zeros, and that's what my final answer looks like. 2.5 times 10 to the minus 11. Now let's try some examples. So the problem says, express in scientific notation. Here we go. The first one, 0.000123. I first take a look at the location of the decimal and I say, where does it need to move to so there's only one non-zero digit on the left? Well, it needs to locate or finish right here. So I say to myself, how many moves is that? Well, that's 1, 2, 3, 4. This is 1.23 times 10. Because I moved that decimal place to the right, it's negative 4. Moving on to 0.080. I need to get my decimal place to this location, so I have that 8 on the left. So it's just a move of 1, 2 spaces to the right. And so my answer is 8. I'm still going to hang on to that 0 that trails to the right, times 10. I moved it 2 spaces to the right, so it's negative 2. On to 0.000000105. Well, if I look to where I need to move the decimal, I need to locate it here once again. So that will place one digit that's non-zero, in other words, a digit from 1 to 9 on the left-hand side of the decimal. Let's count. 1, 2, 3, 4, 5, 6, 7 spaces I've moved that. That is 1.05 times 10 to the negative 7. Now this next one looks like it might be in scientific notation, but once again, the digit to the left of the decimal place right now is a 0. We don't want that. We want it to be 1 to 9. So here we go. We need to move this decimal place so it is finishing here between the 2 and the 5. Watch. 1, 2. And so what we have to do is write our 2.5, and we look at this exponent right here. This exponent is already negative 9. Well, because we moved that decimal place 2 places to the right, we must drop it 2 more units. So it needs to move to be negative 11. And so this is 2.5 times 10 to the negative 11. That works in reverse. If we have 17.5 times 10 to the negative 6, well, I have 2 digits, or in other words, the number 17, to the left of the decimal. I only want 1 digit. So I need to move that decimal 1 place actually to the left. Well, moving it 1 place to the left takes the exponent, and instead of dropping it, increases it. So I'm going to take that negative 6 and move it to be -5. So I'm going up by 1. And so my final answer on this one is 1.75 times 10 to the -5. You may ask yourself, why would we have numbers expressed as they are in D and E? Well, when I look at D, D is actually related to the first question we started with. To write 0.025 times 10 to the -9 is saying that the diameter of the hydrogen atom is 0.025 nanometers. This right here would be the nanometer unit that we would use. That implies nanometers. And sometimes it's more convenient to represent numbers that way. But effectively, all of these are now in scientific notation. They're in finished scientific notation form. That pretty much wraps up both large numbers and small numbers. In our next video, we'll look at doing some arithmetic with them. So otherwise, I'm out of time. Thanks for watching.